Very good morning to all of you. My name is B. Madhava. Currently, I am working as an assistant professor in the Department of Triple BBRUs. So, in this semester, my concerned subject is power system architecture. Power system architecture. So, this power system architecture is for second triple E first semester students. This is for second triple E first semester students, especially for R19 regulation, who are belongs to JNTU Anandapur. So my concern subject is power system architecture. So before we are going to this power system architecture, first we will introduce and discuss the concept or a subject power system. This power system is a very interesting and important core subject for every electrical engineering students. For every electrical engineering students, this is very much essential. So, what is this power system? So here you are already know about a system. What is mean by system? A system means interconnection of components in a sequential manner to get a desired output or desired performance. So here power system means it is also a system but which is a large interconnected system which involves so many of components. Those components are called power system components. Those components are called power system components to perform power generation, power transmission, and power distribution. That's why the power system can be defined as this. The power system is a network which can consist of power generation, power transmission, and power distribution systems. This is the basic definition of power systems. So then after, what are the main components of power system? Power system means this system is constructed for the generation of electric power, transmission of electric power, and distribution of electric power to the various types of consumers. And now, to achieve these performance like generation, transmission, and distribution, what are the main components are required for the power system? Means synchronous generators for the generation of electrical energy in the generating system. Next, power transformer to step up the generating voltages in a generating stations. Next, overhead line conductors to transmit electric power from the generating systems to the distribution system. That means these overhead line conductors are included in a transmission system. Next, distribution transformer. These are used in distribution system to distribute electric power or voltage for different types of consumers in the distribution system. Next, feeder. These feeders are the conductors to transmit electric power or to distribute electric power from one place to another place in a distribution system. Next, motors, lightning, and heating loads. These are the different types of loads which are exist in our distribution system. Along with all these components of power system, some protective equipments are also used These are called switchgear equipments like circuit breakers, fuses, relays, and etc. These are the main components of a power system for the generation of electric power, transmission of electric power, and the distribution of electric power to different types of consumers. So next, our main subject, that is power system architecture. What is meant by power system architecture? Nothing is there. It is very simple. Power system architecture means, which is a design practice of a power system. That's why the basic definition of a power system architecture is the design practice of power system is called power system architecture. Here, the designing of a power system is not an important thing here. That designed power system should provide a better technical performance with approximately 100% energy conversion efficiency in the generating system, transmission efficiency in the transmission system, and finally distribution efficiency in the distribution system. And at the same time, this type of technical performance can be achieved at low cost of power system construction. Such a type of a design practice is called power system architecture. Here, a design practice means interconnection and a location of a power system components selection is called design practice of a power system. Means here, in the generating system, transmission system, distribution system, the interconnection of a power system components is very much essential to produce better power, better energy conversion from the generating station, and to transmit maximum power to the transmission system, and to distribute electrical power without any losses. Better interconnection of power system components selection is required. At the same time, the optimal location of these power system components is also essential to achieve a better technical performance with a 100% energy conversion and a transmission and a distribution at low cost of operation of these power system components. There is very much essential for the interconnection and location of a power system components selection. This interconnection and location of power system components selection is called design practice of a power system. Such a design practice of a power system is called power system architecture. Such a design practice is called power system architecture. So here in this power system architecture, before we are going to discuss about the architecture of a power system or design practice of power system or how to interconnect different types of power system components and their optimal location in the power system, first we will discuss the basic structure of a power system to survive power generation, power transmission, and power distribution. That's why we will go for the power system structure. So here, if you can see here, this is a basic power system structure. We already discussed the power system is which is a large interconnected system which is having three subsystems. Those are power generation system, transmission system, and a distribution system. So here, that's why if we can consider a generating system, this generating system main purpose is to generate electrical energy from other sources of energy. In this generating system, the main component is synchronous generator, which is a large synchronous generator which is used to convert mechanical energy into electrical energy, which is collaborated in the generating station like a thermal, hydro, and nuclear generating stations. So here we can generate electrical energy. What is the necessity to generate electrical energy? To utilize that electrical energy. Where we can utilize that electrical energy means at the load centers. Load centers means domestic applications, commercial applications, industrial applications. Domestic applications means household application. Commercial means shops, restaurants, theaters. Industries means we have different types of industries. So that means in order to utilize the electrical energy at the consumer side, we want to generate the electrical energy first. Because the electrical energy is never be created according to law of conservation of energy. It is converted from other forms. That's why the conversion of electrical energy from other forms is collaborated in generating stations. But these generating stations never nearer to the load centers or consumer terminals or utility systems. These are always far away from the consumer terminals. Because of in the generating stations, the electrical energy can be generated from other forms of energies like coal, gas, nuclear energies, like water energy. So that's why these type of energy sources are available their own places from their sources. That's why these generating stations are constructed where these energy resources are available. That's why the generating stations are very far from the utility systems or consumer terminals for our houses, for our shops, restaurants, theaters, and for our industries. That's why there is a necessity to transmit electric power from generating stations to the consumer terminals. Generating stations to the consumer terminals. That's why a transmission system is exist in between generating station to the distribution system. This is the generation, this is the distribution. In between, there is a large distance. To overcome this much of a distance, the energy can be transmitted from generating stations to the distribution system with the help of transmission system. But this transmission system requires high voltage transmission to achieve bulk amount of power over a long distance, or simply to overcome the losses in the transmission system. Because of this transmission system carries the electrical energy transmission with the help of overhead line conductors. These overhead line conductors are having resistance. Due to resistance, what happens? I square R losses takes place. If I square R losses takes place, output power can be reduced. When output power can be reduced, the transmitter power can also reduce. To overcome this problem, high voltage transmission system is required. When the transmission system is at high voltage, the current can be reduced. The transmitter current, the operator current can be reduced. When transmitted current can be reduced, I square R losses are reduced because of these I square R losses are proportional to the current. When it is this current is at low, I square R losses are also low, then transmitted efficiency or transmitted power is low. But this high voltage transmission is which is involved at a 400 kV, 220 kV, 132 kV or 120 kV. In our advanced countries, they are having 600 kV, 765 kV, nowadays updated version 1200 kV also there. But the problem is here the transmission system is connected to the generating system. The generating system voltage can be delivered to the transmission system, but the transmission system requires high voltage, but the generating system does not have these 400 kV, 220 kV, 132 kV, 600 kV, 765 kV, 400 kV. That is the main problem. That's why there is a need to step up the generating voltage. Our maximum generating voltage in our India is 11 kV, but in advanced countries it is 33 kV. It is 33. But the high voltage transmission requires 400, 220, 130, 600, 765, 400. So for this purpose, we can use power transformers in the generating stations. So these power transformers are the step-up transformers. Step-up transformers means these are step-up the generated voltages from 33 kV and 11 kV to the our desired high voltage transmission level. That is either 400 kV, that is either 220 kV, that is either 132 kV, 600, 765 or 400. That's why there is a need of step-up transformer in the generating system. That's why the main components in the generating system are synchronous generators, synchronous generators to convert mechanical energy into electrical energy, and step-up transformers, or which are also called as power transformer, to step up the generating voltages. And these step-up voltages are transmitted with the help of transmission system. The transmission system having overhead line conductors. The generated voltage can be transmitted through this overhead line conductors at high voltage like 400 kV, 220 kV, 132. But at our consumer terminals, at our utility system, the consumers never use this much of 400 kV, 220 kV, 132 kV, 600 kV, 765 kV, 1200 kV. They can use, their usage can be stored at 66 kV. Large consumers or very large consumers are used 66 kV. Large consumers are used 33 kV. Medium consumers 66 kV, very large consumers, 33 kV large consumers, 11 kV or 3.3 kV medium consumers, and smaller consumers are used 440 volts, not kV, 440 volts, 3-phase power supply. And these are also small consumers which are involved in the domestic applications and commercial shops application. Those are having 220 volts single phase. That means these are the different types of consumers. That means these consumers are never used high voltage transmission level. That's why there is a necessity to step down the transmitting voltages at the end of a transmission line. That's why at the end of a transmission line, one substation is there, that is called city outcut substation. At this substation, the transmitted voltage are stepped down from 400 kV or 132 kV or 200 kV, 222 kV, 600 kV to 66 kV or 33 kV. And the transmission system which is connected from generating stations to the city outcut substation is called primary transmission system, which is having 400 kV, 200 kV. At the end of this transmission system, step down transformer is there in its own substation, city outcut substation, which can step down the voltage from 400 kV, 200 kV, 120 kV, 600 kV to 66 kV or 33 kV. At this substation, large industrial consumers are there, very large industrial consumers, 66 kV. And after this 66 kV, large consumers are also there, 33 kV, large consumers and medium consumers, 11 kV are also. That's why again there is a need to step down the 66 kV into 33 kV or 11 kV or 11 kV. That's why there is a need to construct a substation at the city center. The substation at the central of city is called central substation. Central substation. So at this central substation, the 66 kV or 33 kV can be converted into 11 kV or 3.3 kV. And the power transmitted from city outcut substation to city central substation is called secondary transmission system or sub transmission system, which can carry 66 kV. Primary transmission system carries 400 kV or 220 kV or 120 kV, 600, 760. Secondary transmission system carries 66 kV, 66 kV or 120 kV, 132 kV. At the city central substation, this 66 kV can be converted into 33 or 11 kV or 3.3 kV. So for the large and medium consumers, that's why you need to convert this 11 kV or 3.3 kV into 440 kV with the help of distribution transformer. These transformers we will see are our starting side of the streams. At this transformer having 440 volts, 3 phase, which are taking the power supply from the feeders. The feeders mean which are the conductors from city central substation to the distribution transformers. These feeders carries 3.3 kV or 440 volts. So feeders are started from city central substation. At this city central substation, the 11 kV or 3.3 kV can be stepped down into 440 volts, 3 phase for small consumers. And this feeder system is called primary distribution system, which can carry 33 kV, 11 kV. And the distribution transformers can be stepped down this 11 kV into 440 for the smaller consumers. This is the primary distribution system. After, from the distribution transformers, 3 phase, 4 wire distribution system is there. This is called secondary distribution system. This distribution system is from distribution transformer to the our street poles. Street poles. So here from this secondary distribution system, we will take single phase. From one phase and one neutral, 220 kV. Some stops and houses are taking the power supply from the secondary distribution system. In the secondary distribution system, 440 volts is there and 220 volts is there. 440 volts is the three-phase converter. 230 volts means only single phase. And primary distribution carries 33 kV, 11 kV with the help of traders. Secondary distribution carries 400 volts or 220 volts with the help of service mains. The conductors which are connected from distribution transformer to the house supply or poles is called service mains. So that means here what happened means here this distribution system can distribute the transmitted voltage for different types of consumers. That means 33 kV consumers, 11 kV consumers, 400 volts consumers. From the power transmission system. That's why this power system has three types of systems. For the generation of electric power, transmission of electric power, distribution of electric power. The transmission system having primary transmission, secondary transmission. In the primary transmission system, 400 kV, 132 kV, 600 kV. This is the main transmission system. In the secondary transmission system, this is a transmission system transmit electric power from main transmission system to the CT substation, central substation for the distribution of power. And the third one is distribution system. This distribution system takes electrical energy or power from the secondary transmission system to distribute electrical energy for different types of consumers. In the distribution system, primary distribution system is there which can carry 33 kV or 11 kV from the central substation to the distribution transformers with the help of feeders. And the secondary distribution system having 400 volts three-phase supply from distribution transformers to the service mains. That means street poles or house supplies and shop supplies with the help of service main. This is a secondary distribution system having 400 volts of three-phase system and a 230 volts per phase means a single phase system. So this is the basic structure of a power system. And now, what are the voltage ratings involved in the power system? What are the voltage ratings involved in the power system? Means the generating voltage ranges in our India 11 kV max, but advanced countries is 33 kV. In our transmission system, the transmission voltage ratings are 66 kV, 110 or 120 kV, 132 kV, 220 kV, 400 kV. Advanced countries having 600 kV, 765 kV, and some advanced countries 1200 kV also there. And in the distribution system, the voltage ratings are 33 kV, 11 kV, or 2.3 kV. This is for primary distribution system. And secondary distribution system is having 400 volts for three phase and 230 volts for single phase. So this is our basic structure of our power system. In this power system structure, we will interconnect the power system components in a selected way, and optimal location is followed. We will achieve better technical performance. This type of design practice is called power system architecture. So what is the need of a power system architecture means simply a good power system architecture provides better technical performance. Better technical performance means energy loss is low. Energy loss is low means we can obtain 100% energy conversion. That is, the efficiency of energy conversion is more, then we can generate more power. And also we can transmit more efficient electric power without any loss. Finally, we can distribute efficient electric power without any distribution loss. And this technical performance can be achieved at a low cost. Is the need of a power system architecture. The advantage of a power system architecture is a better technical performance at a low cost. So in this video, we will discuss what is meant by power system architecture, what is the need of a power system architecture, what is the basic structure of a power system, what are the voltage ratings. In the next video, we will discuss what is the importance of electrical energy generation and what are the different types of energy sources to convert electrical energy from those energy sources. Thank you.